In this chapter, we will review multivariate functions and we will learn how to compute partial derivatives. In a multivariate function, we represent one dependent variable as a function of many independent variables. For example, here, z depends on x, y, and w. This is pretty important when we want to represent production and consumption. For example, here, the cost depends on the inputs, which are labor, capital, and land. And in this case, we have that the utility depends on three goods. Normally in economics, we want to see the effect of one of the variables over the dependent variable. In that sense, we use the ceteris paribus property. This means that we will evaluate only one variable at a time, and the others will be considered constant. To understand this concept, let's assume that the function z only depends on two variables, x and y. This is known as bivariate function. In the previous units, we learned how to take the first order derivative for a univariate function. Here, we will apply the same principle for the bivariate function. However, in order to obtain the first order derivative, the other variable will remain constant. For example, here we are taking the derivative of z with respect to x. In that sense, y will remain constant. And this is represented by y, and at the top of the y we will write a dot. This is the principle of ceteris paribus. We only vary one variable at a time. The other will remain constant. For example, here we are taking the derivative of z with respect to y. In that case, x is a variable that will remain constant. Notice that the representation of the derivative can be using this symbol or simply referring as z and x as a subscript when we are taking the derivative with respect to x, and z subscript y when we are taking the derivative of z with respect to y. Notice that the symbol here is pretty important. To understand how we use the ceteris paribus property and how we compute partial derivatives, let's solve these two examples in which we need to take the partial derivatives with respect to x and y in both cases. Let's take the derivative of z with respect to x first. In that case, y stays constant. So in order to do that, we look for the terms that have x. For example, here we have 4x squared and 5x squared y cubic. The other two, as you can see, there is no x. So think that y is a number. Now notice the following. We write the number, which is 4, and then we take the derivative of the variable with respect to x. plus 5. Now notice that y cubic is a constant. So we treat it as a number. And then we take the derivative, again, only of the variable part. Because these last two terms do not contain x, this is 0. It's like taking the derivative of two numbers. Then Zx is equals to 4 times derivative of x squared with respect to x is simply 2x plus 5y cubic, and the same thing here. The derivative of x squared with respect to x is 2x. And this is equals to 8x plus 5 times 2 is 10 x y cubic. Now let's take the derivative of z with respect to y. This means that x is constant. The first term doesn't contain y, therefore the derivative is automatically 0. For the second term, 5x squared is a constant part. And finally, we take the derivative of y cubic with respect to x. Plus, in this case, 8 is a constant part times the derivative of y with respect to y. And finally, plus 7 is simply a number, so the derivative is 0. This means that zy is equals to 5x squared. Then the derivative of y cubic is 3y squared plus 8. Derivative of y with respect to y is simply 1. So this is 15x squared y squared plus 8. Now let's continue with the second example. The derivative of z with respect to x. Let's first identify which terms contain x, which in this case are these three. Now, for the first term, the constant part is 2y. So we are taking simply the derivative of x with respect to x, plus. For the second term, the constant part will be 2 log of y, and we are taking the derivative of 1 over x with respect to x. Minus, notice that in the last part, y is a constant. So we are taking the derivative of e to the 2x plus 2 with respect to x. As you notice, what I'm doing right now is simply isolating x. because it's a variable that we will take the derivative of. So this is two y times 1 plus 2 log of y. Now remember that 1 over x is a very special case because this is going to be like x to the minus 1. So remember that if that is true, then the derivative is minus x to the minus 2. Minus y. Now notice that this is an exponential function. And in the case of the exponential, we take the derivative of the exponent, that is 2, because that is the coefficient of 2x, times e to the 2x plus 2. Now let's simplify a little bit more. So this is 2y minus 2x to the minus 2 log of y minus 2y e to the 2x plus 2. So that is the derivative of z with respect to x. Now let's take the derivative with respect to y. Y appears here, here, and here in this function. Notice that I'm putting yellow, so in that way you can identify what part will be variable in each term. So in this case, the constant part is 2x, and we are taking the derivative of this y with respect to y plus 2 over x. Here we are taking the derivative of log of y with respect to y minus, here the constant part is e to the 2x plus 2, and we are taking the derivative of y with respect to y. So this is 2x times 1 plus 2 over x. Remember that the derivative of log of y is simply 1 over y minus e to the 2x plus 2 times 1. In that sense, the derivative of z with respect to y is 2x plus 2 over x times y minus e to the 2x plus 2.